Let's talk about Raman effect. And what we have here is that when a photon of some frequency, say nu, when it falls on a molecule, the molecule emits a photon having frequency nu 2. Say, for example, different from nu, or let me call it as nu 1. The energy of the emitted photon can be greater, it can be less than that of the incident photon. So this nu 2, if I multiply it with h, so h nu 2 can either be greater than h nu 1, or this h nu 2 can be less than that of h nu 1. Now, as a result of this, the state of the molecule uh, undergoes a change. In particular, the vibrational or rotational state of this molecule. And, and these states of the molecule can change. And what we have is the scattering of light. We have the scattering of light by this molecule. Now, this scattering basically is resulting in the frequency change because we have a different frequency and we have a different frequency. This change in frequency that occurs to the radiation, this change in frequency leads to what's called as Raman effect. And it was discovered by C.V. Raman, and that too in 1982. Now, the scattered light that we have here, it may contain other frequencies besides the frequency of the incident radiation. And the changes in the frequencies that we will have, nu 1, nu 2, and nu 3, will be basically the characteristic of the substance that's scattering the radiation that is allowed to fall on it. Now, let us have a rough idea about the experimental setup of Raman effect. I'll try to go with it. What we have is we have we have a transparent substance by virtue of which, by means of which this Raman effect can be achieved. Now, what we have is we have to go with the setup, a rough estimate of a setup. Let us have a tube C. It's basically a Pyrex glass. It's made of Pyrex glass, and this tube is filled with some experimental transparent medium, and one end of this tube uh, can be put as say W here, is a plane which transmits the scattered light. So from this end we have the scattered light, and the other end that we have is it is projected outwards. I mean, it's projected outwards in the shape of a horn. It's projected like this. So we have, and this horn-like structure is black painted. So it is painted with black paint. So we have black paint here. And this tube C that we have, it's placed in some water jacket that can absorb the overheating system. So what we have here is we have a water jacket. And what else we have is a mercury arc lamp and a glass. And what after that is that we have the focusing lens. I mean, we have the focusing lenses here. What we receive from here is focused, and then we have uh, then we have a spectrograph. So we have a spectrograph. And there is another important thing over here is what we have here is that the tube that this tube C is it is it is enclosed by a chemical, and that chemical is sodium nitrate. And this tube behaves like a cylindrical lens and transmitting the light of wavelength of the order of, in the original experiment, it's 4358 angstrom only. And, and this wavelength only from the light obtained from the mercury lamp and focuses it at the axis of this tube that we have. We have to focus this all light on the axis of this tube. And for that, what we have is we make sure that there are some reflectors. Yeah, it's a reflector. We have a reflector over here. Okay, so this is a reflector, and we have the reflectors from both sides, and we have these reflectors from both the sides. So these are my reflectors, which are focusing this radiation on the tube. And and uh, and the scattered light that we have now. Now, what's happening is that they are, which is basically the reflector around this tube C. It increases the intensity of the light that focuses on the tube that we have here, and the scattered light is focused at the slit. So now we have the scattered light, it's focused on the slit of the spectrograph. And this focusing is done by the lenses. And we can think of using a lens here. And these are the collimators where we can have the beam, the focused beam. Now, in the spectrograph, what we do is we obtain the Raman spectrum. On the either side of the some central intense line. So what kind of spectrum we obtain is something like this. We have something like this, and we find some central line. Okay, so what happens here is that the scattered light, when we have focused it on the spectrograph, in the spectrograph we obtain a Raman spectrum on the either side of this central intense line. The wavelength of this central line is same as that of the incident light. So it certainly has to do everything with the Rayleigh line. So we call it Rayleigh line. So this line is a Rayleigh line. And the wavelength of Raman lines on the other side of the central line with shorter frequency than that of the incident line. We call them as anti-strokes. So we have some additional lines from this side, and their frequency that we have is greater than 0. Their wave number is greater than 0. And what we call them as anti-strokes. Anti-Stokes. And whereas wavelength of the lines that we find on the other side of the central line is longer, and that means than that of the incident line. And we call these lines as Stokes. These lines are called as Stokes. And in this case, the delta nu baud is less than 0. So what we have is we have a Rayleigh line, and we have some other lines to the left of this Rayleigh line, whom we call as anti-strokes, and we find some other lines on the right side of this Rayleigh line. We call them as Stokes. Now, Raman lines are fainter. As I said, it's a very solid line. They are fainter than Rayleigh line, and the frequency or the wave number difference between Rayleigh line and Raman line is independent of the frequency of the incident light. It does not depend on the frequency of light that we have used in the experiment, but is basically the characteristic of the substance that we have used for the scattering. And this kind of thing is being related to its vibrational or rotational transition of the atoms or the molecules that substance is made of. Now, to have some literal line on it, if we think quantum mechanically on this on the outcomes of this experiment, we can certainly picture the incident light of frequency nu. We have the incident light, and it has the frequency nu. As a stream of the photons, each of energy will be h nu. Now, these photons undergo collisions, so they have collisions with molecules. Now, if the collisions are perfectly elastic, so if we have elastic collisions, that means both momentum as well as the kinetic energy of the particles is conserved. In that case, what we will have, there will be no exchange of energy between the molecules and the striking photons. And later simply deflects without any change in the frequency. So it deflects because there is conservation of momentum, conservation of kinetic energy. So there is deflection of this photon, but this deflection does not result in any kind of exchange of energy between the molecules. However, some collisions in the same experiment may also result in exchange of energy between the molecule and the photon. And those collisions can be inelastic collisions, and these inelastic collisions we can talk about them. We can talk about them with some presentation over here. If I have to have, let me go with some baseline. These are the baselines, and let me have a transition and transition. And if I have a transition like this, well, I'll call this A, and I will have a transition like this, where we have some baseline, and I have a transition like this, and then let me call this B, and then I have a transition. I have a transition like this, and this. I'll call this C, and this will be the lowest excited electronic energy level as a reference, and then we have the energy of molecule and photon complex. Now let's talk about this. What we imagine here is that for extremely short periods, a photon is near a molecule during the collision. Okay, and the two together form a sort of complex having an energy difference, or energy different from that of any of the molecular energy levels. And after the photon has moved away, it's almost like that the molecule will return to the level where it was before the collision. In such a case, the photon energy is not changed by the collision, and we have a Rayleigh scattering type of thing that's to be demonstrated here. Now, there is also a small probability if the molecule was initially in the lowest vibrational state or vibrational level, so that nu was zero at that time. Now, after interacting with the photon, it will be in the next higher vibrational state, say nu equal to 1, and 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 it has absorbed and it has gone to the next excited state. Now, the scattered photon in this case will have lost some energy, and this energy will be equal to the energy gained by the molecule and will consequently be of lower frequency. And there is again a very small probability that a molecule which is initially in the nu is equal to 1 state or level, and after interaction with the photon, it will move to a state nu is equal to 0. It will go to the 0 level. The energy lost by the molecule is gained by the scattered photon at ordinary temperatures. So only a small number of molecules can be in the state nu equal to 1 level, whereas majority of them will exist in nu is equal to 0 level. Therefore, for a pair or Raman lines having the same value of frequency shift, the line with frequency higher than the incident frequency, which we call as anti-Stokes line, will be weaker than that one with the reduced frequency line, which we call as Stokes line. So this could be the probable explanation of having those additional lines that can be observed in the experiment, which was originally performed by the great physicist of India, Professor C.V. Raman.